So segment 4 of chapter 2. So we left off talking about the cations of transition elements. All right, so transition metals, again, we're in the center of the periodic table. They're much less reactive than groups 1 and 2. They still transfer electrons, though, to the nonmetals to form their ionic compounds. All right, so that's still what's going on with that. The number of electrons transferred is a little less clear here. So what we're saying is in group 1A, it was guaranteed 1 electron. Group 2A was 2 electrons. For transition elements, it's going to vary on how many electrons are going to go. So they can form more than one positive ion for most cases. There are a few that they're kind of locked in. For instance, zinc is always a +2. Cadmium, which is right underneath the zinc, it's a +2. Silver is a +1. But for the most part, you can have more than one charge on your metal, right? So that means like if I take iron and I mix it with chlorine, well, I'm going to get a mixture of FeCl2 and FeCl3, right? So, and that's because iron can make a +2 charge or it can make a +3 charge. Now, cations of the post-transition metals, so gallium, indium, tin, thallium, lead, okay, this section down in here is what we're talking about. After the transition metals and before the metalloids, those are the ones we're speaking to. It's two very important ones, tin and lead, right? They're very very abundant. That's the word I'm looking for. There's quite a few compounds that have tin and lead in them, and both of these have two oxidation states. It can either be a +2 or a +4, right? So ionic compounds of tin and oxygen are going to be SNO and SNO2. So if it's a +2 tin, then it's SNO. If it's a +4 tin, then you get SNO2. Bismuth only has a +3 charge. Okay, so again, some of them are locked in, some of them are not. It gets a little bit memorizationable, I guess, would probably be the best way to get through it. But I don't really want you guys memorizing things. So again, what you're going to do most times is you're going to use the compound to figure out what the charge is of that transition metal or that post-transition metal. Right. So ions of some of the transition metals and post-transition metals, titanium can be +2, +3, +4. Chromium has a couple of options there. Iron has a couple of options. You can see zinc, like I said, only has one option. It's going to be +2. Silver, cadmium also, only one option each. Bismuth, one option each. So compounds with polyatomic ions. So far we've talked about binary compounds, where we've just had one metal and one nonmetal. But compounds formed from two different elements, right? Now, polyatomic ions means many ions. And so ions composed of two or more atoms linked by molecular bonds. So we've already seen them. We saw an example with the nitrate, the NO3, and the hydroxide, the OH. Now, if the ions are negative, that means they have too many electrons, right? And so if ions are positive, that means they have too few electrons. So formulas for ionic compounds containing polyatomic ions, they'll follow same rules as ionic compounds. So polyatomic ions are expressed in parentheses, right? So we saw that already. We said, I think it was, I want to say it was iron 3 nitrate we had. So it was Fe, and then the NO3 was in parentheses. The parentheses are telling you that that's a nitrate, okay? So it moves as a unit. Now here are some of your polyatomics. You have ammonium ion, we have hydroxide, cyanide. These are all very common ones. This is giving us a plethora of just options here. Now, for us, I've provided down in the student resources a polyatomic sheet. And that polyatomic sheet, now that's not a guarantee that all of my polyatomics for 150 will come from there, but that's the majority of the most common ones that I use. So for exams and things of that nature, naming, you want to make sure you have a good grip on that sheet. So, and they're all, like I said, they're common ones: sulfate, sulfite, phosphate, phosphite, some of the most popular polyatomic ions. All right, so what is the formula of the ionic compound formed between ammonium and phosphate ions? So again, I don't expect you to memorize all the names and all the formulas for polyatomics. So you can look those up. So ammonium is going to be NH4 plus, and phosphate is going to be PO4 3 minus. Now, just like we did with the single binaries, right? So the binary where we have one metal, one non-metal, we crisscross those charges. We can do the same thing with the polyatomics, except now we're going to stay on the outside of the parenthesis, right? So the 3 from the phosphate will go to the outside of the parenthesis for the NH4, and the 1 from the NH4 will go to the outside of the parenthesis for the PO4. Now at this point, because we only have one phosphate, we don't need to keep the parentheses for that one. So when we go to write this out, we're going to write it as NH4 in parentheses. Now we needed that parenthesis because that 3. If we take the parentheses away there, you can see it's going to look like nitrogen, hydrogen 43, phosphorus, oxygen 4. And we definitely don't want it to say that, right? We want to have 3 of the ammoniums, the NH4. Now, since we only had the one phosphate, you can see there we got rid of those parentheses. Now, if you leave your parentheses on, that's not something I'll necessarily mark off for. It might be something I'll have to go back and check on an exam, because a lot of times it's going to be case sensitive when you're taking a test on D2L. If I have it grade automatically, it's going to be looking for you to have it correct without the parenthesis. Right, so that might be something I might have to go in and check on, or you have to look over yourself on your exam. All right, so between strontium ion and nitrate ion, so now we have a single metal strontium and then a polyatomic nitrate. So strontium we would look up, that's in group 2A, it's a +2. Nitrate, we'd pull off our formula sheet, or we plug it into Google, one of the two. We crisscross those, we get Sr2+, and then of course the NO3 we'll put in parentheses. We'll crisscross, and again we have one strontium, and then we have NO3 in parentheses 2, telling us we have 2 nitrates. All right, last but not least, we want to get through nomenclature, which is simply naming. Now the IUPAC system is a standard way of naming the chemical compounds, right? We have one system so that anyone can reconstruct a formula from a name. So again, I don't want you to memorize formulas or names. What I want you to do is be able to learn how to use the system, and that way you can name anything. We will look at naming ionic compounds of representative metals, transition metals, monatomic ions, polyatomic ions, and hydrates. So, naming ionic compounds. For the cations, a metal that only forms one positive ion, then basically you're using the English name for that metal, right? And that's what you've already been doing. So Na+, for instance, is just sodium. Ca2+, that would just be calcium. Metal that forms more than one positive ion, we're going to have some sort of stock system to make sure we do this right. Now the way we do it is we take the cation name, which is the English name, followed by a numerical value for the charge written as a Roman numeral. So hopefully you know your Roman numerals. All right. It's not letting me pull up the pen here. I'm just going to try to pull the pen up. You can use the pen through here. I don't like this pen as much. But basically you need to know your Roman numerals. So you have 1, 2, and of course these are capital I's. Right. 3 would be 3 I's. Totally did not leave myself enough space. 4 would be the one that comes before 5. So 5 is a V in Roman numerals. And then 6 is the one after 5. So it'd be a V and then an I. Okay, that's pretty much all that we need. We don't usually go past 6. So let's see, turn that off. So for our transition metals then, if we have chromium +2, we would say chromium 2. And we'd have the Roman numeral 2 there in parentheses. If it was chromium 3+, then we would say chromium 3. And again, it's pointing out there's no spaces there. So it'd be the name, parenthesis, charge, close parenthesis. Right? So naming ionic compounds then, for the anions, the monatomic anions always end in "ide." So hydride, carbide, silicide, nitride, phosphide, arsenide, telluride, oxide, sulfide. Right? Polyatomics, you'll use the names from the table or from that page that you can get from the student resources. All right, so let's name the following. So we have K2O. So we have a metal that's a non-transition metal, so we simply name it. That's going to be potassium. And then oxygen because it's monatomic, becomes oxide. We put those together and we get potassium oxide. So here we have NH4 and then ClO3. So NH4 is going to be ammonium, and that's going to be a polyatomic name. ClO3 is also a polyatomic, and that's going to be chlorate. And now I'm just going to take those two polyatomic names and I'm going to put them together. So I get ammonium chlorate. For the third one, we have magnesium, which is just a regular metal, so it doesn't need any kind of Roman numerals. That's just going to be magnesium. And then the C2H3O2, it's in parentheses, so right away I know that that's a polyatomic. So I'm going to go look on my list. It turns out that that's going to be acetate. And then I'm going to put those two together, and I'm going to get magnesium acetate. All right, for number 4 here we have chromium. Now chromium is a transition metal, so I'm going to have to figure out what the charge of the metal is. And so the way I'm going to do that is I'm going to base that solely off the anion. So the anion has a fixed charge. This is going to be oxygen. Oxygen is in group 6A, so it's a -2. And since there's 3 of them, that's going to be a total of -6. So that means I have to balance a -6 charge, but I have 2 chromiums to do that. So I'm going to take that -6. I'm simply going to turn the sign because chromium needs to balance it, so it's got to be +6. And then I'm going to divide that by 2. So that means this is going to be chromium 3. Right? So each chromium here has a +3 charge, and so it's going to be chromium 3 oxide. Okay. Now for our last one here, we have zinc, and then we have Br2. Now zinc is also a transition metal, but remember it has a fixed charge. So zinc's charge does not vary. Zinc is either going to be elemental or it's going to be +2. Those are our only 2 options. And so here we have bromine, and bromine is a -1, and so bromine is going to become bromide, and so it becomes zinc bromide. All right, so learning check, determining your formulas. So calcium hydroxide. I'll give you a second here. You can pause if you need to. And hopefully you came up with CaOH in parentheses 2. How about manganese 2 bromide? And hopefully MnBr2. Right, the Roman numeral 2 tells us the manganese is a +2. We know bromine is a -1, and we can crisscross those. All right, ammonium phosphate. Now here you're going to need that polyatomic sheet. So you're either going to have to look up these pieces or memorize them. I don't recommend memorizing them, but if you do, you do. NH43, PO4. All right, the phosphate's a -3. We're going to crisscross that to the outside of the parenthesis. Mercury 1 nitride. Right, now mercury 1 is actually a polyatomic, so that can mess with us a little bit. So we get Hg2, right, it's mercury 1. And then we'll need 3 of those to balance the nitride. All right, which is the correct name for Cu2S? So we have copper sulfide, copper 2 sulfide, copper 2 sulfate, copper 1 sulfide, copper 1 sulfite. All right, so we know it's going to be sulfide because of the sulfur. So that leaves us with A, B, or D. So we just need to figure out what's the charge on that copper. We know it can't be A because we know we need to know the charge of the copper, right? Copper is a transition metal, and so we need to know the charge of that. And since the sulfur is a -2 and both coppers have to be a total of +2, each copper must be a +1. And so D would be our final answer. All right, which is the correct formula for ammonium sulfite? Ammonium sulfite. Well, sulfite, ITE, is telling us that it's got to be an SO3 ending. So you can look on your polyatomic sheet there. We know that we have to deal with SO3, which means our answers are either A or B. The next thing I do is find the charge on sulfite, and sulfite's a -2. The charge on ammonium is +1, so when I crisscross those, I'm going to need 2 ammoniums, which means my answer should be B. All right, so naming hydrates then. So again, they're ionic compounds. So remember, it's an ionic crystal that's got water trapped in its crystal, so that it makes a pretty crystal rather than just a amorphous solid. We have fixed proportions relative to the ionic substance. So naming is just like naming an ionic compound. Then we'll give the number of water molecules and formula using Greek prefixes. So if you remember your Greek prefixes, you have mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And you'll need those for a couple other situations in chemistry as well. So if you don't know those first 10, you probably want to get those down. All right, so here's CaSO4, 2H2O. So first, we don't worry about that hydrate. So the 2H2O doesn't matter for the first part of the name. What we're going to be focusing on is just the ionic compound itself. So we have CaSO4, and Ca is calcium, and calcium's in group 2A, so it's just a +2. We don't have to worry about any kind of Roman numerals. That's just calcium. SO4, of course, is a polyatomic, and so SO4 is on our list as sulfate. So we put that together and we get calcium sulfate. Now, because it's a hydrate, now I'm going to name the water portion. And so the water portion is where we get the word hydrate from. And then how many hydrates do we have? Well, we have 2, which means it's going to be dihydrate. And so we get calcium sulfate dihydrate. All right, how about COCl2 with 6H2O? All right, you can pause here if you need to. You want to work that out. But you should arrive at cobalt 2 chloride and then hexahydrate. Right, cobalt 2 chloride. And that's because the chlorines reach -1. And so that means I need a total of +2 to balance that. I only have 1 cobalt, so that cobalt has to be a +2. So that gives me cobalt 2 chloride. And then of course we have 6 waters, and that's going to be hexa, so hexahydrate. How about FeI3, 3H2O? Again, I'll give you a second if you need to pause. And then for this, we're going to get 3 iodines, each at -1. So the iron has to be a +3 to balance that. It is a transition metal, so it's going to need the Roman numeral. And so we get iron 3 iodide and then trihydrate. All right. So what is the correct formula for copper 2 sulfate pentahydrate? So I'll give you a moment here. All right, it's a pentahydrate. So that limits it down to B, D, or E. It's copper 2 sulfate, so we know we need SO4, which leaves us with only, at that point, E. There it is, copper 2 sulfate pentahydrate. All right, what is the correct name for FeNO3 3.9H2O? So, what's the charge on nitrate? Nitrate's a polyatomic. The parentheses tell us to go look at that list. It's a -1 for each one of those. That's going to give us a total of -3. That means the iron has to be a +3. So we have iron 3 nitrate. And then how many waters? And the prefix there is going to be nona. So we have iron 3 nitrate, nonahydrate, which would be B. All right. So next we want to look at molecular compounds. That means we're going to be focusing on the molecules. Now, electrically neutral particle consists of 2 or more atoms. Now, the bonds here are a little different. The attractions that hold them together in molecules are not going to be from opposite charges. Here, we're going to be sharing electrons. In fact, a lot of times the 2 keywords we look at in bonding is ionic compounds transfer, the keyword transfer the electrons, whereas in molecules and covalent bonding, we're going to share the electrons. So transfer versus share. Right? Ionic compounds transfer, covalent compounds share. Now, a group of atoms that make up a molecule behave as a single particle. So this is not a repeating array of ions. Okay? That's a big difference. So we're not looking at necessarily the smallest number based on the whole number ratio. Right? What we're looking at here is a definite edge. So these molecules are connected to each other, these atoms are connected to each other, and so they have a stop and an end point for our molecule. Now the molecules could form a never-ending array, that could happen, but in a general sense, we have a definite molecule and it stops there. So molecular formulas then describe the composition of the molecule. The subscripts still specify the number of each type of atom present. Okay, so molecules versus ionic compounds. For molecules, we have discrete units. For instance, water equals 2 hydrogen atoms bonded to 1 oxygen atom. For the ionic compound, they're packed as close as they can possibly get to each other. So for instance, sodium chloride would be 6 anions surrounding each cation, and again 6 cations surrounding each anion. No one ion belongs. In other words, there's no true connection between the ions themselves. Okay, so it's not like this sodium is connected to that chlorine, right? Hopefully that makes sense. The sodium is in the center of a bunch of chlorines, and each chlorine is in the center of a bunch of sodiums, right? We don't know whose electron went where. In a bond, a covalent bond, a molecule, we do know who's connected to who. Okay, so that's going to give us molecular compounds. Now they're formed when nonmetals combine, so we're always going to have 2 nonmetals for our molecular compounds. Now, millions of compounds can form from just a few nonmetals, and that's going to get us into organic chemistry and even biochemistry. Now in this course, we won't touch too much in there. We are going to get you familiar with your organic naming, the general organic naming, but you would spend an entire year of courses, so 2 semester courses of organic chemistry typically, and then another 1 to 2 semesters of biochemistry depending on what your actual goal was at the end. Now for these two, we deal with the chemistry of carbon and hydrogen, nitrogen and oxygen, right? Now a few compounds have only 2 atoms. We call those diatomics, like HCl, CO, HF, NO. But most molecules are going to be way more complex than that, especially in the organic world. We can look at just sucrose, like a sugar. We already saw that once. You might be familiar with glucose, C6H12O6. There's urea, right? So we can get into the biochemical pieces of that and get into amino acids, things of that nature, right? So hydrogen-containing compounds, for nonmetal hydrogens, you get the molecule containing a nonmetal and a hydrogen. The number of hydrogens that combine with a nonmetal equals the number of spaces from nonmetal to noble gas in a periodic table. So nitrogen, for instance, is going to have 3 hydrogens. Oxygen is going to have 2 hydrogens. Fluorine is going to have 1 hydrogen. Okay, 3D shapes of molecules. Again, same idea here. Space-filling models, we've seen this. We used to give these the shapes of simple nonmetal hydrides, where blue is going to be nitrogen and red is oxygen. Yellow can be fluorine. And of course the white would be the hydrogen. And so here we can see the nitrogen has its 3 hydrogens, water has its 2 hydrogens, and then the fluorine has its 1 hydrogen. All right. From there we'll get a little bit into organic compounds. So I'm going to stop here. We'll call this one the end of segment, and then we'll pick up with organic compounds.